Hi, everybody. So I thought we could take a look at the review stations for this last chapter unit test we're having that covers volumes, L'Hopital's rule, and relative rates of growth. Okay, station one. And of course, if you haven't done the stations yet, you should probably go do the stations and then come here and watch this. Because if you don't, this makes me get more comfortable with calculus and will not really be getting you as comfortable with calculus as you need to be. Station 1. Find the volume of the region bounded by y equals 0, y equals x squared on 1 to 2. Around the y-axis with shells. Okay, so this is our region, and we're going to rotate this region around the y-axis, and we've been asked to use shells, so I'm going to draw something parallel to the axis of rotation. If there's an ordered pair here, x, y, then this is x and this is y, so it looks like radius is x and height is y. This is a dx thickness we've got here. That's a horizontal thickness, so it's dx. I'd like to get rid of that then, but luckily I know that y equals x squared. So h can be x squared. So we're doing shells. We should have the integral from 1 to 2 of 2 pi x times x squared dx, or 2 pi integral 1 to 2 of x to the third dx. Well, that's a pretty fast x to the fourth over 4 antiderivative that we'd like to evaluate from 1 to 2. I'm going to have 2 pi. 2 to the fourth is 16 over 4 is 4, and 1 to the fourth is 1 over 4. So 16 fourths minus 1 fourth is 15 fourths, 2 times. So we're going to have 30 pi over 4, which reduces to 15 pi over 2 units cubed. Here's my volume, and oh, don't circle your answer. Okay. Station 2. Station 2 has us using that same region, this time about the y-axis. This time about the y-axis with washers. And this is, I think, a much harder problem, because while the big R is always 2, there's a challenge with the little r. And sometimes people aren't looking sort of at the whole picture. They're just looking where they draw the line. If I draw this line perpendicular to the axis of rotation down here, or down here, or here, I think that little r is a constant. But if I draw my lines up here, then I see that little r is a changing quantity, right? I mean, that's not the same as that. So, what's happening here? Well, we've got two different little r's. We have one little r, which is good from 0 to 1. And we have another little r that's good from 1 to 4. Yeah, and so you'd have to write this as two separate things, right? We've got 2 minus 1 for y between 0 and 1. But we've got this other little r, and this other little r is x for the y equals x squared curve. And that means square root of y is x. So little r is square root of y. So then I'd have to set this up as 0 to 1 with that, which would be 2 squared minus 1 squared, dx, plus the integral from 1 to 4 of 2 squared minus square root of y. squared dy. Sorry, that's a dy. Square root of y squared. Good. So that's what I'm looking at. Oh my goodness, I would so much rather use a shell. 4 minus 1 is 3. The antiderivative of 3 is 3x from 0 to 1. Oh, sorry, 3y. It's a dy integral. Plus, here we've got 4. The antiderivative of 4 is 4y. And square root of y squared is just going to be minus y from 1 to 4. Well, that can be tidied up to 3y. Huh. Well, isn't that interesting? That's not at all what I expected. Oh, and that's because this is y, and the antiderivative is y squared over 2. There we go. 4y. That's much better. So, let's evaluate. I plug in my 0, I get 0. I plug in my 1, I get 3. So this is going to be 3. And then over here, 4 times 4 is 16. 16 over 2 is 8. 16 minus 8 is 8. And if I plug in a 1, I get 4 minus 1 half, or 8 halves minus 1 half, which is 7 halves. Okay. Yes. And I sort of lost track there. Let me do that again. So 3, 1 minus 3, 0 plus 4 times 4 minus 4 squared over 2 minus 4 times 1 minus 1 over 2. Okay, so that's going to be 3 plus 8 minus 7 halves, and that's 11 minus 7 halves. 22 minus 7 is 15 halves. Now, don't forget, this was big R minus little r. I was supposed to have a pi with each of those integrals. There we go. And that's, in fact, the same answer we got the other way. And so one thing I might say is, if you're going and checking your answers on the test or on any test, maybe you want to use these two different methods to check each other. Okay. 3, find the volume, same region, rotate it around the x-axis. Okay. So we've got this region, but this time we're going around the x-axis. Well, here we're asked to do that. Oh, it doesn't specify a method. Cool. Well, I think I want to use disks. I know the radius is my y value, also known as x squared. And I'm integrating from 1 to 2 pi r squared dx. So that's pi 1 to 2. Our radius is our y value, or x squared, and so x squared squared is x to the 4th dx. That's going to give me pi x to the 5th over 5 from 1 to 2. 32 pi over 5 minus 1 5 pi is 31 pi over 5. And that seemed pretty easy, pretty straightforward. Let's take a brief cautionary look if we wanted to do this with shells. So I draw something parallel. See, look. In this case, the height is changing. Getting smaller and smaller as I head up here, getting bigger until I get down to here. So in this situation, h is not a constant. But if we look down here, if we look here, h is a constant. And so I'd have to split this up into two integrals. This is the point 1, 1. This is the 0.24. So I have to have 2 pi RH from 0 to 1 dy plus 1 to 4. Yes, I still need that 2 pi RH dy. Now the radius here, the radius is my y value. Is that also true here? Yes, it's also true here. So r equals y in both cases. H is going to be different though. Up here, my height, if this is x and this is 4, my height is going to be 4 minus x. But since this is a dy integral, I need h equals 4 minus root y. Okay, but what about the h down here? Well, the h down here is a constant, 2 minus 1 or 1. Okay, so then I guess I could write 0, 1, y times 1 dy plus 2 pi integral 1 to 4. The radius is still y, but the height now is 4 minus root y dy. And then I would evaluate both of those, but wow, this is so much harder. Hey, a heads up, if you end up finding yourself in a position like this, distribute, and then when you have that y root y, you've got to recognize that as y to the 1 times y to the 1/2, so you get y to the 3/2. It's going to be much easier to do this integral as 4y minus y to the 3/2 than with some sort of, undoing product rule kind of thing. No, I'm not going to evaluate this. That's a lot of time when really I would like to instead be saying, don't do that problem that way. Use those disks. Okay, station 4. No, yes, station 4. We've got the volume, y equals x to the 3rd, from -1 to 1, whose cross-sections are perpendicular to the x-axis are squares. So I'm drawing squares. Now, what I do know is that the squares I draw here and the squares I draw over here, they're going to be the same. And so really, instead of integrating from -1 to 1 in this situation, I'm going to do 2 times 0 to 1. I see that these are slicing the x-axis, so I know these will be dx integrals. And I know that I'm integrating area, and the area for our squares is side squared. Okay, what's this side length? Well, if I have an ordered pair here of x, y, this distance is x, and this distance is y. So I think my side length is my y value, and in this function, the y value is x to the 3rd. So side squared is x to the 3rd squared, or x to the 6th. So I'm going to do 2 times the integral from 0 to 1 of x to the 6th dx. Because all I'm doing is integrating side squared. And the side is the y value, x to the 3rd. Yep, I like that. So we've got 2 x to the 7th over 7 from 0 to 1. I plug in my 1, I get 2/7. I plug in my 0, I get 0. So 2/7 is my answer. And I'm moving on to station 5. Station 5 says find the volume region bounded by x-axis and y equals e to the x on 0 to 1. And so this is our region, and we're rotating it around the y-axis. Okay, so do you want to do disks and washers? No, because I don't have the same right function each time. And that's going to be a problem if I try and do this with washers, because this little r again and this little r is 0. There's no little r here. I've just got a big R. Yeah. So disks and washers? No, I don't think so. because that requires two integrals. Instead, I'm going to look here at using cylindrical shells. Draw something parallel to the axis of rotation, make my two circles at either end of that segment. I see that my height is changing. My height is always this y value, and my radius is that x value. So I feel like I'm going 0 to 1, 2 pi r h dx is going to become 0 to 1, 2 pi x times y dx. Okay, so I've got to get rid of that. Oh, but I know that y equals e to the x. Aha, so this is going to be 0 to 1, 2 pi x e to the x dx. And even if I take that 2 pi out, I'm still looking at something that's a little uncomfortable. I see a function and someone else's derivative, or I see a function and someone else's derivative. And that tells me that even though this is a much easier problem than doing it with disks and washers, I still have to do some thoughtful integration. So I'm doing by parts here, and I get this. So this is going to be x e to the x minus the integral of e to the x dx. And so I can say then that I've got 2 pi x e to the x minus the antiderivative of e to the x is e to the x. And I'd like to evaluate this from 0 to 1. Okay, if I plug a 1 in here, I get e minus e times 2 pi minus 2 pi times, if I plug a 0 in here, I get 0 minus e to the 0 minus e to the 0. Well, e to the 0 is 1. I have minus minus, which is plus 1 times 2 pi is 2 pi. And so my volume here would be 2 pi units cubed. Okay. 6. 6 says I should use my calculator. We're taking that same region, 0 to 1, and we're rotating around the line x equals 3. We're not told whether or not to use shells or disks and washers, so I'm going to do shells. So it looks like this is my radius, and this is my height. It looks like my height is my y value. Radius isn't x. This is x. This is 3. So radius is 3 minus x. We know that y is e to the x. Okay, so, and remember, when we integrate, we're only integrating the region. So I'm going to start at 0, but I'm going to stop at 1. I'm not going to integrate all the way to 3. Only integrating the region. So 0 to 1, 2 pi, 3 minus x, e to the x dx. This is definitely by parts. I don't need a calculator for that. I wonder, I just kind of wonder what we would get if we did suffer through that other approach. Got that. All right. I'm drawing something that is perpendicular to the axis of rotation. I see a little r. I see a big R. Big R. Okay, so my little r down here is 3 minus 1, or 2. And my big R is a constant 3. So when I integrate 3 squared minus 2 squared dy from 0 to 1, yeah. That would be 9 minus 4, or I'm integrating from 0 to 1, 5 dy. Okay, but what about from here to here? Okay, so this is x equals 1, and this will be e to the 1, which is e. So I'm integrating from 1 to e. Now in this situation, big R is still 3, but little r, no. sorry, big R is not still 3. I don't know what made me say that. I can try the picture again. Okay. We've got this region. We're doing this part up here now, about the line x equals 3. And still my little r is 3 minus 2. Little r is 3 minus 2, or 1. Now, what about my big R? That's very interesting. Now I kind of want to go back and look at that. Because that's 1, that's 3, isn't it? Oh, no, it's 1. So that's going to be 1. 9 minus 1 is 8. Okay. So that little r is 3 minus 1, or 2. Good. And what about big R? Well, big R is this. This is x. This is 3. Right, so we have big R is 3 minus x. But this is a dy integral. We know that y equals e to the x, which means x equals ln of y. So this is going to be 3 minus ln of y squared minus 2 squared dy. So I need this integral plus this integral. No, sorry, I need these two integrals. This is 0 to 1, this is 1 to e. That just looks horrible. I would so much prefer to do this one, even with a calculator. Okay. Oh, you wanted that with calculator, did you? Okay, we were going from 0 to 1. We had 2 pi. We were saying that radius, this is x, and this is 3. And so radius is 3 minus x, and our height is our y value, and our y value is e to the x. So I'm integrating 3 minus x e to the x dx, and I should be able to do this on the calculator. Math, integrate, oops, math, integrate 3 minus x times e to the x, comma x, comma 0, comma 1. And that gives me, what is that as a fraction? No, it doesn't want to make it into a fraction. Okay, times 2 pi. 2 pi. Okay, 26.106 is what I got. I want to do it by hand. 3 minus x, 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 e to the x. So 2 pi x, 3 minus x, minus the integral of e to the x, which is e to the x. We're evaluating that from 0 to 1. That's going to be 2 pi 3 e to the x minus x e to the x minus 1 e to the x. And so I can combine my terms. 2 pi 2 e to the x minus x e to the x. Yeah, really don't want to evaluate that way. I would much prefer 2 pi e to the x, 2 minus x, from 0 to 1. Okay, if I plug in a 1, I get e, 2 minus 1 is 1, 1 times e, so 2 pi e minus, I plug in a 0. 2 minus 0 is 2, I plug in a 0, I get e to the 0 is 1, 2 pi times 2 is 4 pi. So 2 pi e minus 4 pi. How about that 4.513 number? That was missing a thing. Yeah, I didn't get that. That is 2 pi times that. If I divide this by 2 pi, I get that number. I think I missed something in one of them. I think one of them is correct, but I'm not sure. I think I should go back and look. I'm sorry. How frustrating for you. Kukla, why can't you just be a perfectionist? Or, Kukla, why are you trying to be a perfectionist? We know you aren't. Well, yeah, okay. So, 3 minus x. This is negative 1 dx. Dx, dx. And we have u dx. And so we have u dx. 3 minus x minus a minus. Because I'm subtracting the integral of this times this. That's going to make all the difference, because now I'm adding an e to the x. So this is plus e to the x. And so now I'm going to have 4 e to the x minus x e to the x. Okay. That's what I'm integrating. No, that is my antiderivative. And I'm going from 0 to 1. Then there should be a 2 pi. Okay, so I plug in my 1, and I have 4e minus, I plug in my 1. I get e, 1 times e, that's going to be e, 2 pi, minus 2 pi. Now let's plug in our 0. E to the 0 is 1. 1 times 4 is 4. And if I plug in a 0 here, that goes away. So, what do I have that? I've got 8 pi e. No, that's 3 e. So that's 6 pi e minus 8 pi. Okay. 6 pi e. 6 pi e minus 8 pi. And that gets me my 26.106. Yay. Okay. See, it really is worth it. And you do learn stuff by like going back and looking for your mistakes. Well, if you're open to it, you do. That was station 6. Station 7. Volume rotating square root of x. X equals 4. 0 to 3. Oh, 0. Okay, so we're taking this region, and we're rotating about y equals negative 3, and we've been asked to use shells. So, I draw something parallel to the axis of rotation. I see that this is my height. This is x. This is 4. So height is 4 minus x. But since these thicknesses are vertical thicknesses, this is going to be a dy integral. And so we know that y equals square root of x. We square both sides. X equals y squared. So this should be 4 minus y squared. Our radius is this plus this, or top minus bottom. So r is y minus a negative 3, or y plus 3. Our radius is this y value plus this 3, or top minus bottom. So now, if I integrate, or I set up my integral, I'm looking for 2 pi y plus 3 times 4 minus y squared dy. And I'm not integrating from 0 to 4, I'm integrating from 0 to 2 because this is dy. Yeah, 0 to 2. Okay. Yeah, no, don't want to use by parts here. I want to FOIL this out. 2 pi, 0 to 2, 4y plus 12 minus y to the third minus 3y squared dy. Okay, so that's going to be 2 pi. The antiderivative here is 2y squared. The antiderivative here is 12y. The antiderivative here is y to the fourth over 4. And the antiderivative here is just y to the third. And we're going to evaluate from 0 to 2. Okay. So if I plug in a 0, all of these things go away. If I plug in a 2, I'm going to have 8 plus 24 minus 2 to the fourth is 16. 16 divided by 4 is 4. And 2 to the third is 8. Okay, so 32 minus 12 is 20 times 2 pi. I get 40 pi. Ta-da! 8. Ooh, now we want to do the same thing using washers. Okay, so we have this region from 0 to 4, going around y equals -3, and I see my inner radius is always 0 minus 3, or 3. But my outer radius is constantly changing. My big R is not always the same, even though I've kind of drawn it so it looks the same. Okay, so what can we say about big R? Well, big R goes from here to here. Big R is this y value and this 3. Big R is top minus bottom, which gives us y plus 3. However, these are dx washers, so I'm going to have to get rid of that y and replace that with square root of x plus 3. Okay, so now my integral will be pi square root of x plus 3 squared minus little r 3 squared dx. And this is dx, so I'm going from 0 to 4. Okay, please don't turn that into x plus 9 minus 9. This is a FOILing situation. You need to FOIL here. So we're going to have pi integral 0 to 4 x plus 6 root x plus 9 minus 9 dx. So yeah, those do cancel. Pi 0 to 4 x plus 6 x to the 1/2 dx. So my antiderivative is going to be x squared over 2 plus, well, this has to become 3/2. And I'm going to bring that 3/2 down, but I don't see 3/2 here. So there must be something present. And that thing that's present is a 4. I bring down that 3/2. 3 times 4 is 12, divided by 2 is 6. And I want to evaluate that from 0 to 4. Okay, so let's plug our 4 in. 4 squared is 16, divided by 2 is 8. Okay, square root of 4 is 2. 2 to the third is 8. 8 times 4 is 32. Now, if we plug in 0, we get 0 and 0. And so I end up with 40 pi, just like I did last time. Okay, yeah, I don't know which of those was easier. What do you think? Station 9. There are 14 stations. Let's take a look at Station 9. Station 9 says y equals x to the third on 0 to 1 perpendicular to x-axis are equilateral triangles. Oh my goodness. Kukla, you're killing me. I hate when you do equilateral triangles. I mean, I appreciate that these equilateral triangles are dx. Thank you for not doing dy. Okay, perpendicular to the x-axis are these. Now, we know that we're integrating area. And we should know the formula for area of an equilateral triangle as a function of its side length. Because I know that many times this year, I've said you should write it down on your formulas to know page. Okay, so if we haven't and we still need this, here are our sides. Here's our altitude, our height. We know the area of this triangle, 1/2 base times height, but we really want to get rid of this and replace this with some s stuff. Well, there's a couple of ways to do this. One is, if I draw this altitude, that means that this is 1/2 s and this is 1/2 s. Now, at this point, I could do this a couple of different ways. I could use the Pythagorean theorem to find h. I could say, oh look, this is an equilateral triangle, therefore this is 60 and 30, and I could use my 30, 60, 90 shortcut, but I am going to have to use one of those, or I could even use trig to find h. I am going to say that I remember in a 30, 60, 90, if I take the short leg and double it, I get the hypotenuse. And if I take the short leg and multiply by √3, I get that height. So h is going to be √3 over 2s. And you should get that value for h if you use the Pythagorean theorem as well. So when I take this and plug it in there, I'm going to have s times s for s squared, and 1/2 times √3 over 2 to get √3 over 4s squared. That's the area of our equilateral triangle. Okay, now, what do I know? Well, I know that the side length is my y value, right? So there's this ordered pair here called xy, and this distance is x, and guess what? This distance is called y. So my side length is y. So I really want y squared. But, wait a minute, what's y equal to? Y equals x to the third. And so y squared is going to be x to the 6th. Okay, so √3 over 4y squared is going to become √3 over 4x to the 6th. Okay, so we're integrating area 0 to 1. What's our area formula? √3 over 4 y squared, which is x to the 3rd squared. And so we can say that that's going to be 0 to 1, 3 over 4, x to the 6th dx. I'm going to pull the constant out and integrate just the x to the 6th, and 3 over 4, x to the 7th over 7, from 0 to 1. Well, if I plug in my 0, I get nothing, and so I'm just going to plug in my 1 and get √3 over 28. There we go. Alright, that was station 9. Ooh, station 10. Ooh, evaluate limits. Station 10. Okay, we've got a limit as x heads to 0 of 1 minus cosine x over x squared. Okay, try the direct substitution first. Cosine of 0 is 1, 1 minus 1 is 0, and I have 0 on the bottom. So if f equals 1 minus cosine x, and g equals x squared, and f of 0 equals g of 0 equals 0, and f prime and g prime exist everywhere. Use L'Hopital's. So let's use L'Hopital's. By the way, this has to happen before you use L'Hopital's. If you put it as an afterthought, You're not getting all the points there, buddy. So no, really, because you need permission to use L'Hopital's rule. And that's this. So L'Hopital's rule, the limit as x heads to 0. Derivative of this is 0. The derivative of negative cosine is sine. And the derivative here is 2x. But if I plug in a 0 on top and bottom, I still end up with 0 again. So, whoops. Okay. Here's L'Hopital's again. Okay. So, I use L'Hopital's rule, and now I have the limit as x heads to 0. Derivative of sine is cosine, and the derivative here is 2. I plug in a 0, cosine of 0 is 1. So I get 1/2. This, problem number 1 on station 10, that limit is equal to 1/2. What about problem number 2? 2 says the limit as x heads to 0 from the positive, square root of x ln of x. Okay, so that's an infinity, well, really a negative infinity, and that's a 0. And so this is that situation where we want to throw one of them into the denominator. And I don't really enjoy throwing that as its reciprocal into the denominator. I think I'd much rather put this upside down in the denominator. But I could be wrong, and I should be ready to, pivot and change my point of view. 1 over root x. Okay, so 1 over root x is x to the minus 1. And when I plug in my zeros here, I get infinity over infinity. Okay, so let's say then that, let's just take a moment though to look at that other path. The limit as x heads to 0 from the positive of square root of x over 1 over ln of x. So here's the thing about doing it this way. I actually think that doing it this way makes for an easier justification. And I mean an easier justification on my brain. My brain thinks it's easier. Because when I plug in the zeros, 1 over infinity is 0. And so I get 0 over 0. So it's easier for me to say that, f equals square root of x, and g equals 1 over ln of x, or ln of x to the negative 1, and f of 0 equals g of 0 equals 0, and f and g prime exist for x greater than 0, then use L'Hopital's. And while I feel that makes for an easier justification sentence, I really don't want to do that derivative. Not that I can't do that derivative, I just don't want it. My issue here is that when I plug in my zeros, I'm going to end up with infinity over infinity. And what's wrong with that? Well, there's nothing really wrong with that, except that f of 0 doesn't exist. So I'm going to do f of 0 from the positive. And f of 0, if this is my f, that's negative infinity. And if I plug in a 0 here, that's 1 over square root of x. Because that's always got to be positive. And that's always got to be positive. Oh, but I can't put negative numbers in it. Yeah, so that's heading towards infinity. So let g of 0 from the positive. So this one's positive infinity, this one's negative infinity, and what am I going to put here? I'm not putting 0, I'd have to put infinity, but maybe I'd have to put plus and minus infinity. Oh, I find that so problematic to write that. Anyway, either way, just come up with some sort of justification. This makes my brain much easier. And then let's go about using L'Hopital's rule. So I'm going to have the limit as x heads to 0 from a positive of 1 over x. And here, if I take the derivative of this, I have negative 1/2 x to the minus 3/2. And I think all I need to do is a little algebra. limit as x heads to 0 from a positive 1 over x times negative, yeah, I'm going to leave that down here for now, and I'm just going to move that one up and be x to the 3 halves. X to the 3 halves. I guess this is x to the minus 1. That's still on the bottom. That should be 1 over x. Yes. Let's do it this way. Let's turn that into x to the minus 1. X to the minus 1, 1 half, x to the minus 3 halves. See, that's what I'm trying to get at. And I'm dividing, and the bases are the same. I subtract the exponents, and so now I'm going to have the limit as x heads to 0 from a positive. So x minus 1 minus a minus 3 halves over negative 1 half. I can do flip and multiply with this, and that'll get me the limit as x heads to 0 from a positive of negative 2 x to the 1 half. If I plug my 0 in here, square root of 0 is 0, 0 times negative 2 is 0. All right, I was able to get the limit there. It's a lot of work for a 0, just saying. I'm glad you're going to need that in Calc 2 when you do convergence. Okay, 3. The limit as x heads to 0 of 1 over x minus cosine x. So if I plug a 0 in here, I have infinity minus 1. And guess what? That's infinity. That's it. Nothing special there. And cosine of 0 as well. Yeah, that's it. Okay, station 11. Looks like more limits to evaluate. The limit as x heads to 0 of cosecant x minus cotangent x. And curiously, this is going to be that infinity minus infinity situation where we said we would usually make a common denominator. So I don't see any fractions, so let's make some fractions. Cosecant is 1 over sine. Cotangent is cosine over sine. Okay, now I see that I already have a common denominator. And so that's going to be 1 minus cosine over sine. Okay, if I plug in a 0, I get 1 minus 1, which is 0 on top and 0 on the bottom. Yes, this is a L'Hopital situation. So we're going to have to write that justification. We're going to say if f equals 1 minus cosine x and g equals sine x, and f of 0 equals 0, and g of 0 also equals 0, and f prime and g prime exist everywhere. Use L'Hopital's. Okay, so I'm going to use L'Hopital's rule on this. I'm now going to have the limit as x heads to 0, derivative of that is 0, the derivative of negative cosine is sine, and down here the derivative of sine is cosine. If I plug in my 0, I end up with 0 over 1 or 0. There we go. Okay. That was problem number 1. Problem number 2 from station 11. The limit as x heads to 0 from a positive of x to the x squared. So this is one of those 0 to the 0 situations where we're going to need to take the ln on both sides. Let's bring these down. We're going to have ln of y equals x squared ln of x. So let's figure out what this limit is. The limit is x heads to 0 from a positive of x squared ln of x. Again, if I plug in my 0, I'm getting that infinity times 0 situation, which means I have to flip one of them into the denominator. And again, the algebra, or the calculus in the algebra, is easier if I do this, 1 over x squared. I think writing the justification is harder because I have that infinity over infinity thing to play with. But certainly the rest of the problem is easier. In fact, I'm just going to use L'Hopital's rule because I already know this is infinity over infinity. And I think I've written the justification enough times for you. And Jen, don't ask, what if they do this in the test? Well, I like to think you'll make a good choice between using the easier algebra and the tougher justification versus the easy justification and the tougher calculus. I think my path is self-evident. So I'm using L'Hopital's, and I'm going to have the limit as x heads to 0 from a positive 1 over x, negative 2 over x to the third. You probably want me to write that out. How did you know that, Mr. Cooper? Well, 1 over x squared is x to the minus 2. And so then y prime is going to be minus 2, x to the minus 3, or minus 2 over x to the third. There it is. Now, if we do a little flip and multiply action, we're now looking at the limit as x heads to 0 from a positive 1 over x times x to the third over negative 2. Great. I can do some canceling here. I can plug in my 0, and I get 0. But remember, this is what the ln y is equal to. And we need to know that y is in fact 1. The limit of, what was this? The limit as x approaches 0 from a positive of x to the x squared power. This is going to be equal to 1. Coming from the positive, you may recall we actually looked at this in the first week in August. We did, I think it was x to the 2x. Remember over here, it kind of looked like a fish hook and undefined there, and then it was doing that thing with the dots on the other side, and that's why we're looking for the positive. From the positive, what y value are we approaching? We're approaching a y value of 1. So I can claim the limit there is 1. Okay. And there's a 3. So the third one says the limit as x heads to 0 of x plus sine x over x plus cosine x. Okay, so please do us a favor and plug in the 0. 0 plus 0. And on the bottom, 0 plus 1. 0 over 1. 0 pizzas divided by u, yeah, that's nothing. That's 0. Do not use L'Hopital's rule here because this is not a L'Hopital's rule situation. L'Hopital's is only for 0 over 0, infinity over infinity. There are those other cases like 0 times infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, infinity to the 0. All of these can be rewritten to be 0 over 0 or infinity over infinity. But this is 0 over 1. That's 0. That's not L'Hopital's. You use L'Hopital's there, you're going to lose a lot of points. And I can see that happening to some people on the test. So, hey, listen up. Don't do that. Okay, station 12. Looks like more limits to evaluate. The limit as x approaches 1 of x, no, of 1 minus x plus ln of x over 1 plus cosine pi x. Oh my goodness. Okay, if I plug in a 1, 1 minus 1 plus 0 is a 0 on top. I plug in a 1 here, cosine of pi is negative 1 plus 1 is 0. Okay. So, if f equals 1 minus x plus ln of x and g equals 1 plus cosine pi x, and f of 1 equals g of 1 equals 0. That's so much easier. And f prime g prime of 1 exists, then use L'Hopital's. Okay, or maybe you want to say use L'Hospital's. Some people really feel that that S is crucial. Okay, L'Hopital's. So let's use L'Hopital's here. That's going to be the limit as x heads to 1 of negative 1 plus 1 over x. And the derivative of this is 0. The derivative of cosine is minus pi sine pi x. Okay, so what happens when we plug in a 1? Okay, sine of pi is 0. So I've got a 0 on the bottom. And 1 over 1 is 1. Negative 1 plus 1 is 1. So we have to use L'Hopital's again. Okay, so let's use L'Hopital's rule. L'Hopital's rule takes the derivative of this. We've got the limit as x heads to 1, negative 1 over x squared. And if I take the derivative of this and add negative pi squared, derivative of, that's a constant, right? That pi times that pi gave me that. So I've already done the inside of the chain rule. I need to say that the derivative of sine is cosine pi x. Okay, let's plug in our 1. So we've got negative 1 over 1. And in the bottom, if I plug in a 1 here, 1 times pi is pi. Cosine of pi is negative 1. Negative 1 times negative pi squared is positive pi squared. And there we go. This was not a problem where I had to, exponentiate, take the log at the beginning. It looks like problem number 3 is going to be like that. This was just, you've got 0, 0, so dig into L'Hopital's rule. 2, though, looks like it's going to be something a little more thrilling in that scary way. 1 plus 3 over x plus 5 over x squared. Hey, Justin, is that a Taylor polynomial? Ooh, raised to a power? Like, Suddenly, I feel very uncomfortable. Bad touch, bad touch. Okay, but I do see function raised to function, and so I'm thinking I'm going to be taking the ln of both sides. Let's just check. 3 over infinity, that's 0. 5 over infinity squared, that's 0. So this is 1 to the infinity. Yep. If y equals 1 plus 3 over x plus 5 over x squared to the x, I'm going to say then that ln of y is x times ln of 1 plus 3 over x plus 5 over x squared. Okay, so now if I consider the limit as x heads to infinity of x times ln 1 plus 3 over x plus 5 over x squared. When I plug my infinities into these places, these turn into 0. ln of 1 is 0, 0 times infinity. And in that 0 times infinity situation, we're going to throw one of them into the denominator. Okay, so now I've got the limit as x heads to infinity of ln 1 plus 3 over x plus 5 over x squared over 1 over x. And again, I really want that from the positive. Okay, so, yeah. This, however, when we plug in, oh no, these are infinities, aren't they? Yeah, these are infinities. I need them to get that to be 0 over 0. Okay, so if f is ln plus 3 over x plus 5 over x squared, and g equals 1 over x, and f of infinity, equals g of infinity equals 0, at least I feel like I have some solace there, and f and f prime and g prime exist for x not equal to 0, then use So what's L'Hopital's going to get? Well, if I take the derivative on top, the derivative of ln of stuff is going to be 1 over stuff times the derivative of stuff. Well, the derivative of that is 0. The derivative of that is minus 3 over x squared. And the derivative of this is minus 10 over x to the third. Okay, that looks kind of scary and uncomfortable. So, I think it's time for some algebra. We've got the limit as x heads to infinity of negative 3 over x squared minus 10 over x to the third over 1 plus 3 over x plus 5 over x squared. Yeah, it really does feel like I should make a common denominator up here and a common denominator down here, and then do a flip and multiply. And suddenly that time that we spent doing complex fractions last year in pre-cal makes a lot more sense. So common denominator, I just need to multiply by x over x. I've got minus 3x minus 10 over x to the third. And down here, it looks like I'm going to have x squared plus 3x plus 5 over x squared. So this is what I'm going to do my flip and multiply with. And that's going to be the limit as x heads to infinity minus 3x minus 10 over x to the third times x squared plus 3x plus 5. Okay, so those cancel 2 of those. And how's it looking now? Well, it still looks like infinity over a whole lot of infinity. Okay, so let's distribute that to these. X to the third plus 3x squared plus 5x. So I'm still getting infinity over infinity, so use L'Hopital's again. And when I do that, the limit as x heads to infinity of negative 3 over 3x squared plus 6x plus 5. Okay, so now I've got infinities down here. I've got 3 over there, and 3 divided by infinity is 0. No pizza for you. But remember, this is ln of y. At the beginning of this problem, I took the ln of both sides. So y equals e to the 0 or 1. That's the value of this limit. Oh my goodness, that was a lot of work. Yeah, well, that's why we saved it for last. And then finally the limit as x heads to infinity of x to the 1 over x. Well, this is going to be that infinity to the 0 situation. So we know if y equals x to the 1 over x, we could then take the ln of both sides. And so we could think about doing this limit instead of x over x. So if I plug, so this is actually harder on the brain than this. And so I'm actually going to do this one. If I plug my infinity, this heads to infinity. 1 over infinity is 0. So I have 0 times infinity, which means I want to set one of these into the denominator upside down. Well, that was this originally, right? Where we had ln of x over x. Oh, wait. Yeah, I could have gotten that. I was just being timid. Oh, now I got dry mouth. Okay, so justification again. Sorry, I'm pouting. Okay, so use L'Hopital's. I just don't want to go to that uncomfortable place. And I now have the limit as x heads to infinity of 1 over x over 1. I plug in my infinity. 1 over infinity gives me 0. And again, remember, this is ln of y equals 0. So y equals 1. All right. That was, station 12. let's take a look at station 13. Ooh, another volume problem. Cross-section is perpendicular to the y-axis. Just when I wanted to get away from limits, you give me this. Good luck. Creature. Perpendicular to the y-axis are squares. Okay, great. So I know that I'm supposed to integrate area, and in this case, that means I need side squared. Well, this is x. This is y. This is x. This is 1. So it looks like my side length is 1 minus x. Okay. Except that this is dy. So I know that x equals cube root of y. So 1 minus cube root of y. But we don't want s, we want s squared. 1 minus y to the 1/3 squared. Which I have to FOIL. 1 minus 2 y to the 1/3 plus y to the 2/3. Yowly! So we're integrating from 0 to 1. Okay, and 1 minus 2 y to the 1/3 plus y to the 2/3 dy. Okay, so what does that give us? Well, the antiderivative of 1, antiderivative here. So I'm going to add 1 there and have 4/3. Yeah? But I don't see a 4/3 here. So if I put 3/4 here, times that minus 2, we can do some canceling. I have minus 3/2. Minus 3/2. So when I bring down the 4/3, the 3's cancel. I cancel here and just end up with a minus 2. Oh, well, that's going to work wonderfully. So, yep, 3/2 here. And then plus, well, I have to add 1 to this. This is going to be y to the 5/3, which means I need a 3/5 here. So when that 5/3 comes down, the 3/5 cancel and gives me just that positive 1. And we're integrating from 0 to 1. Now, if I plug in 0, that'll go away. If I plug in 1, 1 minus 3/2 plus 3/5. You can, for free response, leave your answer like that. But if it's multiple choice, we're going to want to go further. We're going to make a common denominator. 10 minus 15 plus 6 over 10. So that's 16 minus 15, which is 1/10. All right, that's my volume. Okay, station. Oh. Hey, remember that thing I always said about make sure you answer the question they're asking? Yeah, I didn't just do that. Because that's the region. And those are our squares. Right. So this is going to be this x value minus this x value. Well, we already know that that one is cube root of y. Cube root of y. But this one is y. I'm using right minus left to tell me what the side length is. So side squared, y to the 1/3 minus y squared. So that's y to the 2/3. This times 2. So minus 2y to the 4/3 plus y squared. Okay, so that's what I'm integrating from 0 to 1. Silly me. Minus 2y to the 4/3 plus y squared dy. Okay. Yeah, it's always good to check your work, check your premise, make sure you're answering the question that they asked. Oh my god, is that useful. So this is going to be y to the 5/3. So I need a 3/5 out in front. Minus this is going to be y to the 7/3. So I want a 3/7 times that minus 2, and it's going to be minus 6/7. And here I need y to the third over 3. And we're going from 0 to 1. Again, when I plug in 0, I just get 0. We plug in 1s, I get 3/5 minus 6/7 plus 1/3. Well, look at that wonderful list of primes. So let's make that common denominator, which is 35 times 3, 105. So 21 times 3 is 63. I need 15 times 6, which is 90, and 35 times 1. So that's 98 minus 90 is 8 over 105. And that's a different answer. See, it really does matter. Okay, so that was 13. And now our last station, station 14. Oh, this time we're doing the same cross-section thing, same squares, but this time we're perpendicular to the x-axis. So our squares look like this. And we can go back to using top minus bottom to find s. So x minus x to the third is our side length. So if we're integrating area from 0 to 1, that's going to be x minus x to the third squared dx. Okay, so that's integral 0 to 1 of x squared minus 2x to the fourth plus x to the sixth dx. Okay. And where does that take us? That takes us to x to the third over 3 minus 2. No, not derivative, antiderivative, you noob. Okay, and plus x to the 7th over 7. And we're going from 0 to 1. Again, if I plug in zeros, nothing. If I plug in 1s, I get 1/3 minus 1 plus 1/7. And I know that's instantly wrong because this is going to give me a negative number. And that's not cool. I think my thought is here. I think that's supposed to be x to the fourth. Not that. Yeah, we had this, and x times x to the third is x to the fourth. Yeah. Try again. Okay. So, antiderivative, x to the third over 3. This is going to be x to the fifth over 5 plus x to the 7th over 7 from 0 to 1. Oh, that feels a lot better. Okay, so we get 1/3 minus 2/5 plus 1/7. Yeah, that's probably going to be positive, but very tiny. Okay, so common denominator time is 105. We're going to have 35 times 1, and 21 times 2 is minus 42. We're going to have 15 times 1, and that's 40, 50, yep, that's 8 over 105. Yay! Units cubed. And so we're done. That's the last of our stations. I hope that you feel well prepared for your test. Take care, everyone.